Now that we have some basic idea that classification will involve identifying some partitioning spaces or subspaces and specifically hyperplanes that can help us classify the objects. Now what we are looking for some mathematical mapping that takes form of F and takes our RD from R, which is parameterized by a vector called as weight vector. Remember that when we were talking about a regression, we were also talking about W1x1 plus W2x2 and so on. And hence we say that this X can be transformed as inner product of W and X, and there would be some constant shift from the origin, which is the perpendicular distance from the origin to the hyperplane that is under consideration. So for example, if we talk about this simple problem in 2 dimensions, we see that there are certain points marked by orange and certain points marked by blue, and there are many possible hyperplanes, and these hyperplanes are not necessarily passing through zeros or through the origin, which for convenience is marked here. So the question that we are arising is that out of this or any of these possible arrangements, what should be the location of that particular hyperplane? But before we really put this as an optimization problem, we have to understand what is the relationship between our weight vector and the hyperplane that is under consideration. Now, when we talk about, let us say that this hyperplane would be separating two classes such that when X belongs to a d-dimensional vector space, then f of X would be equal to 0. That would mean that if we take any point that is or any vector which is lying along this particular hyperplane under consideration, the f of X plus b should be equal to 0. That means that would define the equation of this specific hyperplane. And when we try to identify the relationship between W and X, what we can do is that let us say that there are two vectors XA and XB that are located along the hyperplane under consideration. Now we just said that if these vectors are lying along the hyperplanes, f of X of A has to be equal to 0, f of X of B has to be equal to 0. If we write f of X of A minus f of X of B, so if we have two vectors, one here and another here, we can clearly see that the closing arm or difference of A and B would align along the hyperplane under consideration. So f of X of A minus B can be written as WXA, their inner product, plus B, because what I am doing, I am substituting the value of X as XA here, and that has to be equal to 0, minus W X of B, their inner product, plus B has to be equal to 0. And when we simplify it, we get it as W times XA minus XB, because W is common in both of these terms, and we know that by the principle of linear bimapping, bilinear mapping, we can write it as W and inner product of XA minus XB. Now, since f of XA is equal to 0, f of XB equal to 0, this implies f of XA minus f of XB has to be equal to 0 by principle of linear superposition, because so far we are still talking about linear mappings or linear transformations, which would imply that the inner product of W and XA minus XB has to be 0. Now, what if this inner product is represented by a simple dot product, and for that matter any kind of inner product, if the inner product is equal to 0, that would mean XA minus XB vector and W vector are orthogonal. And what that would mean, that since XA and XB, they are lying along the hyperplane is always perpendicular to the weight vector that is under consideration, and we are essentially looking for the weight vector in the problem of support vector machines that can help us come up with some functional mapping that help us separate these two classes that are under consideration. Now the question arises which line we should go for. Should we go for this, that, or any other line that we have not drawn here? So essentially this becomes an optimization problem. In our last lecture, we talked about we will look for a line that will separate the margins. So that line should be drawn in a way that it is farther away from both these points so that it is happily able to deal with surprises. Let us say tomorrow a new point comes here which is classified as red or belongs to an orange category marked as red here. Our classifier would still work fine, but it is very much closer to the boundary. So if we change our classifier to this line, you can clearly see that all the points, although they belong to the orange class, they all would be classified wrong because we have no margin of error. So when we said that SVM is essentially the problem of maximizing the margin, this is what we mean, that hyperplane should be located in a way such that the margin is always there to let us minimize the errors that we are making on classification. Now also one thing is for sure, since we say that fx is equal to 0 exactly at hyperplane, then there would be certain cases which are marked as positive and certain cases that are marked as negative, carrying the example from our good weather bad weather problem. Now that is for clear that for all the points that are on one side, we should have fx to be greater than equal to 0 when their actual class of y is positive 1. That, and we are saying that only two classes are possible which will represent it with +1 and -1, and this should be true for all n's. So x 1 2 3 for all the way till n, this should be true. Similarly here we can say that fx should be less than 0, and we are taking the boundary case in favor of positive. You can always write fx less than equal to 0 and then this would be just greater than 0 when yn is equal to -1. Hence, our problem can be objectively stated as that we are training the classifier where we want to ensure that the wxn plus b should always be greater than 0 when yn is equal to +1 and wxn plus b is less than 0 when yn equal to -1. Mind it, when I'm saying wx, we are talking about the inner product, which we will later substitute with the simple dot product, but without loss of generality, it's always better to write it as an inner product between weight and the x vector under consideration. So we can combine these two things because you see that this yn when multiplied by wxn, their inner product, plus b, it has to be greater than or equal to 0 in both cases, because if we multiply this particular yn by this equation, it becomes greater than 0 and yn would have value of -1. Similarly here, this is positive and hence this sign will remain unchanged. So we can write equation A and equation B in the compact form as yn as wxn plus b greater than equal to 0. Now in this case we are not talking about the optimality. We are just saying that this condition has to be met, and that makes sense from here. If you look at all of these classifiers that we have drawn on this simple example, all the points which are on right side of all these hyperplanes, wx plus b is definitely greater than equal to 0, and for all the points for all these classifiers, wx plus b is less than 0. But our biggest question is still remain unanswered. Should we go with this classifier or this classifier or this classifier? And in case of mathematics, we really want a closed form solution, which is the unique solution as well as the optimal solution for our problem. And in next lecture, we will talk about the traditional derivation of SVM, that how we can derive that unique solution that tells us, yes, this should be our hyperplane for the best possible separation of various points. Minded, I am motivating this example using two class problem. Same concept would generalize to n class problem. And also, if you have n classes, you will have n minus 1 hyperplanes. If you have two classes, as in this example, we will only have one hyperplane separating these classes. In next lecture, we will continue with our derivation. Thank you.